Every single second, millions of us open up a digital map. We search for a restaurant, try to navigate our way out of rush hour traffic, or simply ask for the absolute fastest way to get where we need to go. And somehow, almost instantly, we get an answer. But here is the massive, invisible problem with that. The world contains billions of roads. If we turn the world into a giant mathematical graph, treating every intersection as a node and every single road as an edge, the sheer scale of the Earth becomes a total computational nightmare. Looking at just the North American road network alone, we're talking about over 64 million intersections.
That's 10 to the power of 220. If you want to drive from New York to San Francisco, this astronomical number represents a simplified estimate of the possible routes you could theoretically take to cross the country. To put that insane scale into perspective, that is vastly larger than the total number of atoms in the observable universe. It is the ultimate needle in a haystack challenge.
Think about it this way. If you built a supercomputer that could check 1 billion different routes every single second, testing all of those combinations would still take over 10 to the 200th power years. The universe itself hasn't existed for even a fraction of that time. And yet, you pull out your phone, type in a destination, and it finds the perfect route in 4 seconds.
So, how is that even physically possible? How can a simple piece of software instantly filter through billions of possibilities to find the absolute perfect path without brute forcing its way through a mathematical eternity? Well, the answer is a fascinating invisible machine. It's a real-time simulation quietly working behind the scenes.
Part 1. The 20-minute algorithm.
Our story actually starts way back in 1956 with a Dutch programmer named Edgar Dijkstra. Now, computers were so incredibly new at the time that when Dijkstra went to file his marriage license, the authorities literally wouldn't accept programmer as a real profession. He was working on this early computer called the Armac, and he needed a problem to demonstrate its power to the general public. While sitting at a cafe terrace in Amsterdam with his fiancée, he conceived the perfect demo. What's the shortest way to travel from Rotterdam to Groningen? In just 20 minutes, without a pencil or paper, he invented a completely elegant routing solution.
Here is the absolute genius of Dijkstra's algorithm. Instead of just blindly guessing, you assign your starting point a cost of 0 distance, and then you assume every other city is infinitely far away. Then, you step out to your immediate neighboring nodes. You update their actual distance cost, mark your starting point as explored, and just repeat the process. Imagine a puddle of water expanding in all directions until it finally touches the destination. By searching from lowest cost to highest, it mathematically guarantees that you have found the absolute shortest route.
Part 2. The need for speed.
Dijkstra's algorithm is stunningly elegant. If you use it to find a route within a single city, say getting across New York, it runs incredibly fast. We're talking about 100 milliseconds. But if we try to route a path across the vast graph of North America, sprawling out equally in every single direction and testing tens of millions of intersections along the way, a well-tuned Dijkstra algorithm takes a sluggish 7 seconds per search. And in computer time, 7 seconds is an absolute eternity.
Now, 7 seconds might sound okay if you're sitting alone in your car, but you aren't the only one asking for directions. You're waiting in line behind millions of other users worldwide. If a server takes 7 seconds per query, the whole system just collapses. To support simultaneous global users, an algorithm actually needs to run in under a single millisecond. It literally needs to be 7,000 times faster.
So engineers naturally tried to give Dijkstra some intuitive shortcuts. Enter the A-star search. Instead of expanding outward blindly in all directions, A-star penalizes moving away from the target. It's kind of like turning the map into a 3D slope where moving away from your destination goes uphill. It aggressively targets the destination, cutting the search space significantly. It is brilliant for things like video game characters and solving mazes.
But A-star ultimately fails us on the open road. It's amazing if you only care about geographic distance. But let's be real, nobody wants the shortest distance, we want the fastest travel time. A highway might be slightly out of your way geographically, but it's far faster than driving in a straight line through 20 local stop signs. When you try to optimize A-star for speed limits rather than straight-line distance, it requires some really complicated heavy math to calculate the difference. And that heavy math instantly destroys the algorithm's speed advantage. It just bogs down completely.
Part 3. The hierarchy shortcut. When you and I drive, we naturally use human intuition. We meander on local roads, hop onto a massive highway for the bulk of the trip, and then hop off back onto local roads at the very end. We instinctively understand road hierarchies. Modern mapping systems had to find a way to encode that human intuition mathematically. On one extreme, we have Dijkstra, which requires zero pre-processing, but takes forever to run. On the other extreme, we could just pre-calculate every possible route ahead of time in a massive lookup table, so that queries are instant. But storing all those paths would take over 8 petabytes of raw data. That's equivalent to storing all of Wikipedia 16 times over. Plus, you'd have to recalculate the whole thing every time there's a traffic jam. We needed a sweet spot right in the middle.
That sweet spot? It's called contraction hierarchies. This right here is the secret sauce. It's an algorithm that mathematically pre-processes a map to automatically rank geographical bottlenecks and create ultra-fast routing shortcuts. There's no more categorizing roads by hand. The math figures it out entirely on its own, discovering the most important structural arteries of a country.
It does this through a really clever process called nested dissection. Think of 2 towns separated by a river, with only one bridge. That bridge is a massive bottleneck, right? Any trip between the towns has to use it. The algorithm looks at all of North America and finds the absolute biggest bottlenecks that literally split the graph in half. It turns out there are about 102 nodes that do this, mostly bridges over the Mississippi River. Those get the highest rank. Then the algorithm cuts the map again, finding the next highest rank, which follows the Ohio River. Then it traces the Appalachian and Rocky Mountains. It recursively splits the map over and over, zooming in until all 64 million nodes are mathematically ranked by their structural importance.
Once this hierarchy is built, the real magic happens. The algorithm calculates and adds mathematical shortcuts between these highly ranked nodes. So when you ask for directions, the system runs a search from both your start point and your destination simultaneously. But here is the trick. It is only allowed to search up the hierarchy. It checks your local roads, jumps immediately to the high-ranking shortcuts, and completely ignores millions of irrelevant side streets across the rest of the country.
The results of this are completely staggering. If you search for a route from San Francisco to Montreal, Dijkstra would have to brutally check millions of individual nodes across the continent. With a contraction hierarchy, the system searches exactly 1,236 nodes. Because once you're on the highway level of the hierarchy, it only needs to check massive bottlenecks like those Mississippi River crossings.
The final, triumphant runtime for a trip across the entire North American continent? 200 microseconds. That is a fraction of a millisecond. It's 35,000 times faster than the original Dijkstra calculation. This customized algorithm cuts the search space down by a factor of over 44,000. This is exactly why maps feel instant today. The data centers have already structurally mapped the country's hierarchy long before you even pulled out your phone.
Part 4. An enduring legacy. The modern digital map is not just a map. It's a living digital model of human movement, processing millions of complex route requests seemingly via magic. Yet, even with petabytes of data, real-time traffic updates from millions of smartphones, and incredibly complex hierarchical math, at its core, this modern miracle is still just Dijkstra's algorithm. For all the theoretical developments in computer science over the last 7 decades, the heart of the system relies entirely on an elegant invention dreamed up in 20 minutes in a 1966 Amsterdam coffee shop.
Dijkstra famously stated, "Simplicity is prerequisite for reliability." He designed his solution without pencil or paper, forcing himself to avoid all avoidable complexities. And because of that brutal simplicity, we have a foundation strong enough to route billions of people globally every single day.
We rely on these massive, hidden engineering systems just to live our daily lives, rarely stopping to think about the invisible logic pulsing beneath the surface. So the next time your phone instantly tells you the fastest route, it leaves us with this final thought. What other invisible modern miracles are quietly running on 70-year-old elegant ideas?